For this section 5.1, areas and distances, we're going to be able to see several features of these antiderivative. Recapping, in the previous chapters, we knew ultimately that if I have a graph of position versus time for anything, it could be a particle, and I knew what the position was at every single time, then by finding derivatives on this graph, I was able to determine what was the velocity for any particular time. So any derivative here to the graph, it will show me how fast the particle was going and in what direction the particle was going. And if I knew the function, I could find the velocity function, and if I knew the velocity function, by applying derivatives or by taking the derivative again, I was able to obtain the acceleration if I wanted to. And if I took the derivative one more time, that was known as jerk, but we really didn't see a lot of that. Now what we're going to do with antiderivatives is one of the things that we're going to be able to do, and this is very interesting, is if I know the velocity of a particle over time, well, definitely in here the derivative will be acceleration. But because I know of antiderivatives, I'm going to be able to find the area between two particular moments. And what would be the meaning of that area numerically? What would be the interpretation of it? If the derivative of velocity is acceleration, what would be the area under the curve for velocity over time? And that would be how much distance the particle has traveled. We're going to be able to find that. We're going to be able to find what is the difference in the position of the particle, how much it has traveled. And this is very interesting because, for example, let's say that the velocity, think about this, was miles per hour and the time was in hours. The multiplication of base times height, let me just redraw this. Let's say that the velocity is constant at 60 miles per hour. So if you know that you travel from hour 4 to hour 6, you know that you have traveled 2 hours. And you know that if you have traveled 2 hours at 60 miles per hour, when you do the multiplication, when you actually find the area of that rectangle, what you're going to get is the distance that you have traveled. So this is something that is consistent with the units of the axis, and also it has a physical meaning. If you have a graph of velocity versus time, then the area under the curve will be the distance traveled, and that's going to be very neat. However, we're not going to deal with functions that are easy as a constant function. We're going to be dealing with functions that have a graph that is not a straight line. Therefore, if we have to find some kind of area under a curve for which we really don't know the formula for, like, first of all, there is no name for this shape, so let alone having a formula for the area of this shape. So we're going to devise a way, and we're going to apply what we have of derivatives to figure out a way to find the area of the region, the area under the curve. And we're going to see different examples. So in general, we have a function that is going to be called f, and some area that we're going to refer to in this section as capital S. And we are going to talk about what happens between points A and B on the x-axis. So in here you have the line x equals A. Remember that for any vertical line, the equation is x equals a number. So this is the line x equals A, this is the line x equals B, this is the function f, and this is the x-axis. So to be able to find this area, we need to know what the boundaries are. So this area is bounded by the lines x equals A, x equals B, the x-axis, and the function. So as I mentioned before, areas under the curves are a little bit more complicated than finding actual areas of shapes. However, we're going to devise methods to find the area under a curve using simple areas like the area of the rectangle, and we will also be using area of a trapezoid. So let's look at example 1, and it says use rectangles to estimate the area under the parabola y equals x squared from 0 to 1. Now in here we really don't know how many rectangles we're going to use to estimate. If you form this, well, this is really not a rectangle, this is a square, but this area is definitely very large compared to the area that we're trying to estimate. So definitely one rectangle, one square will not do our estimation. Now we could do 2 at 0.5. So I'm trying to approximate this area plus this area using 2 rectangles. So the question now is, well, will my rectangles have this as height? Okay, one of them, and the other one will have this one as the height. Or will I use the left side of the rectangle as the height? So in this case, the height of this rectangle is 0, and here the height of this rectangle is this much. So as you can see, let me do 2 examples here. So I have, if I'm using 2 rectangles for which the base is 0.5, the rectangle that I'll be forming here is gonna be greater than the actual area that I'm trying to use, but it's an estimate, so it's okay. That could be one option. Or the other option that I have is having the same situation, having the same number of rectangles, 2 rectangles, but now the height, instead of being the side on the right side, it's going to be the side on the left side. So in here the height is 0, so this rectangle has base 0.5 and height 0, and then for the second rectangle this will be the height. So as you notice, if I'm using, in every rectangle, if I'm using the right side as the height, or in this case the left side as the height, I will be either overestimating or underestimating the actual area that I'm trying to find. So the question becomes, okay, so how many rectangles it is optimal to actually find an estimate that is close enough? So what would be the picture with 4 rectangles? Let's say that I want to do 4 rectangles to divide this area. So if I have the same area and now I'm using 4 rectangles, then every rectangle will have a base that is worth 0.25. So this is 0.25, this is 0.5, this is 0.75, and that is 1. So I'm going to show you when we're using the left side as the height and when we're using the right side, and 1. So if I'm using the right side, then if this is the base, this is the right side of the base, so I draw a height. The height will stop where the function is, and that's where I construct my rectangle. Now this is a base, this is the right end of the base. I drop a line until I'm touching the graph, and that will be F, and then I'm forming my second rectangle. Then again, this is the base of my third rectangle, this is the right side, there is a vertical line, and then that's how tall my rectangle will be. And then the last one is going to be as tall as this, and that will be it. So this area, the sum of these 4 rectangles, would be an estimate of the function that I'm trying to find. So let's find out how much is that actually is that actual estimate. So I have 0.25 times the height of this rectangle is actually f of 0.25 plus, again, the base of this rectangle is again 0.25, and I'm going to multiply it by the height of the second rectangle, which is, if this is 0.5, then this will be f of 0.5 plus, again, the third rectangle has the same base, And now the height will be f of 0.75, and then I'm gonna add the area of the last rectangle, which will be the same base, and the height will be f of 1. Now remember that f is x squared, so it would be 0.25 times 0.25 squared plus 0.25 times 0.5 squared, and so on. What would it be like, I'm going to find this numerical value now. What would it be like to use the left side of the base as the height? So let's look at this. This is the first rectangle. This is the left side of the base of the first rectangle. Now the height is 0, so there is no rectangle here to be shown. On the second rectangle, this is the left side of this mini base. So I'm going to drop a line, and now I'm going to go this direction. And this is the area of the second rectangle I'm going to find. Now on the third rectangle, this is the left side. I hit the function, and then I'm forming my third rectangle. This is the fourth rectangle that I'm going to form. This is the base. This is the left side of the base. And then I touch the function, and that is the fourth rectangle that I'm forming, knowing that the first one is really not a rectangle because the height is 0. So as you can see, the sum of these three areas quite not cover the area that I'm trying to find. This is an underestimate. I'm estimating below of the actual area that I'm trying to find. So now let's see how we're calculating the area of this side. It will be 0.25 times f of 0, and you know that f of 0 is 0. That's why that area really is not shown, because there is nothing there, plus 0.25, that's the base of this rectangle, times the height, f of 0.25, plus 0.25 times f of 0.5 plus 0.25. Don't confuse that with a little 5, 0.75. So let's just compare the two different ways that I have to find an estimate on this function, on the area under this function. If you compare one by one, you can see that in this case, when I'm using the right end of this rectangle as the height, I'm using the right end of each interval in here. I'm using 0.25, 0.5, 0.75, 1. And in here, if I'm using the left side, I'm actually using the left side of every interval. If I have 4 intervals, I'm using 0. I'm using 0.25, 0.5, and 0.75. I'm not using f of 1 in here. And that's okay, because if I have 4 areas and I have 4 rectangles, then that's all I need to find the estimate for the area under the curve. And these two numbers are going to be different. So let's look at how much they are. So overestimating with right-sided rectangles, I have 0.46875, and when I'm using left-sided rectangles, I'm having 0.21875. So if I want to make a good estimate, I'm going to have to find out what would be an overestimate and underestimate, and maybe I can take the average of these two numbers, and that will be an estimate of this area. But we're going to learn different ways of making better estimates of this. But right now we're just exploring to see what happens. We saw the situation when we were using 2 rectangles. What we saw right now, I'm using 4 rectangles. And then we're going to see what happens with a different number of rectangles. So you can see here, in this figure, we're using 8 rectangles. So this one is using the right end points, or the right side of the rectangles as the height, and then in here is using the left end points. So you know that this is going to be an underestimate, and this is going to be an overestimate, and it's because these rectangles do not quite cover the area S that I'm trying to find, and this one covered too much, is covering that, and it's covering more. So this is something that you're not going to be asked to do for different number of rectangles, but this is just to show you what's the point of this part. We can do the same thing with 10 rectangles, 20, 30, 50, 100, and 1,000. Now, this is a little bit of notation. R sub n means the sum of the rectangles generated by using the right endpoints of the intervals on the x-axis, and L sub n is by using the left endpoints. So these are, for this particular curve, these are x squared. These are underestimates, and these are overestimates of this. So for 10 rectangles, this is the difference. For 20, this is the difference. Now look at for 1,000. These two numbers are getting very close to the actual region S. So you can see that the more rectangles that you use, the closer you're going to be to the actual number. So for 1,000 rectangles, if you take the average, then this will be a number that is a lot closer to the actual area than any of the other estimates. And so visually, what you're going to see is that the more rectangles that we generate, the areas that we're finding, even if we're overestimating or underestimating, the area of the rectangles altogether is getting closer and closer to the actual area of the region that we're trying to find. So you know that the more rectangles we have, the better estimate we have. So if instead of 1,000 rectangles we have infinite amount of rectangles, then the area will be closer to the exact value. Since we're trying to use infinite amount of rectangles, you know that this is going to be tied somehow to limits. Yay! See, you were absolutely right. So the area that you're trying to find is going to be the limit as n approaches infinity of the sum of all those rectangles. You want to have as many rectangles as you possibly can. So by looking at the numbers, you know how to find limits. If we have a table, you know how these numbers, the more rectangles I have, is kind of approaching the number 0.33. So the actual limit is actually 1/3, which is 0.3, and repeating. So let's just now get into what's going to be the actual definition of these area problems and what it is that we are going to do with that. So for example, in general, I have this function, and I'm trying to split it into some number of rectangles, which I don't know. I'm just trying to define them in a general way, because you know that we're going to apply limits, so we have to find a way of generally describe them. So it says the width of the interval between two numbers is the difference between those two, so it's B minus A. So the width of each of, if we have n strips, if we have n rectangles, then definitely how wide each one of them is the difference, or the space between B and A divided by the number of rectangles we have. So this is something that we're going to describe as delta x. That's the space in between each height. That's the base of the rectangle. Then it says the strips divide the interval AB into n subintervals, which means they are smaller intervals than the original one. So the intervals are going to be called between x sub 0, or the initial x sub 1, between x sub 1 and x sub 2, between x sub 2 and x sub 3, and so on. Because you have n intervals, then the last x that you're using is going to be called x sub n. And it says, well, x sub 0 was the original value A that you have, and the last one that you're using, x sub n, is the number B that you have at the end. So it says the right endpoints of the subintervals are, so you know that x sub 1 is obtained by having x sub 0, or the initial value that you have, A, and you're adding 1 delta x. How do you get x sub 2? X sub 2, you get it by having the initial value and adding 2 delta x's. Remember that each of these bases is delta x. How do you get x sub 3? You're adding 3 delta x's. And that's all it's saying in here. So now it says if we're going to approximate the area of each rectangle, then it has to be by right points, it has to be defined by doing base times height. So for example, if I want to find the area of the third rectangle right here, then I have to do the base, which is delta x, times the height. So to write the sum of all the rectangles using the right endpoints will be, for every base I'm using the point on the right, the height will be f of that x, in this case x sub 1 times delta x. And you can notice how this sum has in common that delta x, because we're dividing this interval into equal interval, into equal length. So the actual area of this region S that we talked about earlier is actual the limit. And if I know how the sum of all the rectangles that I have using the right endpoints, if I have an expression like that, then finding this limit is actually possible. The way it is right now, I can't find it because I don't know what f is. I'm going to have to know what f is actually to be able to define this limit. But as definition, the area that we were talking about under the graph of f is the actual limit as n approaches infinity of the entire sum. This is the first rectangle, this is the second rectangle, this is the nth rectangle. Now we can apply this definition to also to the left endpoint, and we're not afraid to do that because we know that as the rectangles get many more, the actual limit is going to make sure that even if it's from the right or from the left, that we're approaching to the correct value. Now notice that if we're using the left endpoints, then the function, the first one that I'm going to use, is evaluated as x sub 0, which will be f of a, and not the first one. And notice how we're not using, in here we're using f of b at the end, f of b times delta x. That's what this term means. In here we're not using f of b, we're using the x that came before that. And it can be shown that if we have all these rectangles, we can not only use the left side or the right side as the height of the rectangle, we can use any x within the interval. In here we're using an x that is very close to the left side, and in here we're using the one in the middle, and in here we're using one that is close to the right endpoint. So the x that is going to be chosen within the interval is going to be called a sample point. So the area under this curve is going to be the limit as n approaches infinity, as f evaluated at that sample point times delta x, and so on. So all those expressions are going to be equivalent.